everyone, let's go ahead and let's go over your homework. You had on page 85 application 1 and 2. So let's go over how to solve those. These are more of your math problems. So if you got stuck on these, make sure that you're paying attention as we go through it. Alright, so let me get the right spot. Alright, calculate the amount of heat needed to raise the temperature of water in a 40-gallon or 151 kilogram home water heater from 19 degrees Celsius or 66.2 degrees Fahrenheit to 60 degrees Celsius or 140 degrees Celsius. Alright, so this one's giving you a lot of information, but a lot of it you don't actually need based on your equation. Alright, if we're working with heat and water and raising temperature, what is the equation so far that we know of? Okay, I have a table to help me out with specific heat, but I have an equation for at least heat, specific heat, mass, and temperature change. What's that equation? You could have put it in two ways. So you could have, I'll write it over here, so I'm going to be over here on the side. Could have written it as C equals QM delta T. But since we're asked to find heat, we need to make it into the different versions. So Q equals CM delta T. Now, you might think, well, wait a minute, it didn't tell me what specific heat was. It's because your book knows you have the table where it has that chart to list it and to figure it out. So, that's how come it tells you specifically that it's water, because it knows you have the table to figure that out. So, make sure as you're going through it, you want to think through and figure out, okay, what am I trying to find? Alright, so we're going to use this equation for it. Now, it's mass, temperature change, and specific heat. Now, what's your units for specific heat? This will tell you and help you to remember which units to use. Alright, so for water, I'm going to write over here now. Water has 4.18 joules per grams degrees Celsius. That's one of the reasons why you want to pay attention to your units, because it lets you know what units to use for it. So if you try to use gallons, which is a side note, we've never used gallons, but if you decided, oh, it gave me gallons, I should use gallons. Nope, your book is just checking to see, okay, are you thinking, do you know what units you're supposed to use? So don't use the gallons one. So 4.18, the grams one or the kilograms one is the one that you need to know for it. Now, since this is joules per grams degrees Celsius, you technically need to put it in grams, not kilograms for it. So, if you didn't do that and you listed it as kilograms, your answer is going to be slightly off. So just make a note though that you want to put it in grams, not kilograms. So if you make a note of, oh, oops, but it's okay. Just make a note of, okay, this is in grams per degree Celsius. You need to put it in grams. Don't leave it in kilograms. So 151 kilograms becomes what in grams? Good job. 151,000 grams. So that's how many grams you have for it. And then degrees Celsius, if you're going from 19 degrees to 60 degrees Celsius, what's the difference? Remember, you want to develop good habits of 60 minus the 19, because remember, it's the final minus the initial. You want to develop good habits now so you'll know if it's a positive or negative value. Since the temperature went from 19 to 60 degrees, did the temperature go up or go down? Right, it went up. So should it be a positive number or a negative number? Positive number, but this just helps you to make sure that you always get that positive number for it, because you don't want to develop bad habits. So the temperature change is positive 41.0. I think that's right on my bar, so I think you can still see it though. So just be careful. So 40.0. So I multiply all of these together. So 4.18 times 1,000. Keep saying 1,000. 151,000 times 41, and that'll give you your total amount of heat that is needed for it. The total amount comes to a very, very, very large number. So the total amount for this is 25. So excuse me. It's, I put my decimal point in the wrong spot. 25,878,000. Oh, I put my decimal point in the wrong spot. Let me rework this out really quick. The book goes ahead and gives it to me in the rounded answer. I want to make sure that I give it in the unrounded answer. Excuse me, I thought I checked this yesterday. Alright. Alright, I was close though. So, 25,878,380. This is why you write neat, so that way you can make sure you can read your answers. Alright, so that's the answer that you get unroundedly. Now, you might be thinking, okay, unrounded or proper sig figs, where should I round to? Alright, so thinking back through it, how do I round this, or how do I get it to how many sig figs? Well, if this one has 3 sig figs, this one has 3 sig figs, this one has 3 sig figs, how many sig figs should my answer have? 3 sig figs, perfect. So 25,900,000 joules would be the proper answer for it. If you want to put it in kilojoules, you just take this number and just divide by 1,000. So divide by 1,000, and that'll give it to you in the kilojoule form. So in the kilojoule form, it just becomes 25,878.38 kilojoules. And so that's the kilojoules answer. That is the full answer. So either answer is fine. You left it in joules or you left it in kilojoules. So just be careful as you're going through it that you're paying attention to your units, and that'll let you know what units you need to keep it in. Alright, let's look at problem number 2 now. Alright, number 2, how much heat is needed to raise the temperature of 1 pound, which again, don't want to use pounds, so 454 grams of aluminum from 25 degrees Celsius to its melting point at 660 with a decimal point degrees Celsius. And then it tells you what the specific heat of aluminum is. So this one, it should have clued you into, oh, since I'm using specific heat, I should probably use one of these 2 equations to help figure this out. Alright, so let's go ahead and let's solve it. So if you realize now, okay, I think I see what I did wrong and I'm going to try this one really quick, pause the video and then work it out yourself. Alright, so let's go through it. So let's figure out the temperature change first. So I'm going from 660 with a decimal point. Now remember, I went from 25 degrees Celsius to 660. So it's 660 minus the 25, so that you develop good habits for it. That comes out to 635 degrees Celsius. So just make sure that you know that with good habits. I put a decimal point. Technically, I didn't have to. I just didn't want to forget. Alright, so the mass for the, there goes my screen. I'll fix that in a minute. Alright, so the mass of aluminum. So it's 454 grams. The specific heat of aluminum is 0.900 joules per gram degrees Celsius times 635 with the temperature in Celsius. So the answer, 454 times 0.9 times 635 comes out to, and then it gives it to you as 259,461 joules. Now, looking at sig figs, how many sig figs should I have? Perfect, 3. So this becomes 259,000. No decimal point, remember, because that way these don't count. Joules. So that becomes the answer for this one. Alright. So if you have trouble with this, be sure to email me and ask me so I can help you out as best as I can and as quick as I can. Alright, for your classwork, it's going to be actually a little bit different. We went over the terms and definitions yesterday, which you should still learn and still know. But I'm going to double check some more of your math processes. So I'm going to slide this over. Try to do it slowly. Alright, I think that's large enough for you to show up and to read on your screen. That's as zoomed in as I can get on it and still have it all fit properly on the screen. So I believe that's as close as I can get for it. Alright, so go ahead and pause the video for it. Alright, number 3, I think it got cut off a little bit, but it's asking what is the delta E for that system, or the change of internal energy. So what equation should you use if you're working with heat and work and internal energy? So think it through and figure out which one should you use. These problems should only take you maybe 5 to 10 minutes to solve. So problems 1, 2, and 3. So this is the first one, this is the second one, this is the third one. Don't worry about these yet, we'll talk about these in a minute. I think that's as zoomed in as I can get and still have it all fit. So go ahead and pause the video and try to solve them on your own. If you want to wait, if you can't read them, I'll read them aloud in a second for you. So if you can't read them, just keep watching and then pause the video as we go through them. But go ahead and try to pause the video. If you get completely stuck, you have no idea what to do, unpause the video and then figure it out, and then watch it as I explain it. But try to think through it. Don't just watch me solve them. You want to get practice solving them on your own. Alright, so this first equation, if I'm working with change of internal energy, because delta E, if we're working with change of internal energy, heat, and work, we only have one equation so far for this. So delta E, still that delta, I don't feel like fixing it though. So Q plus W. Remember delta E, delta means change, E means internal energy, Q means heat, W means work. So just make sure you know all those things for it. So that's the equation we're going to use for it. That delta makes me sad. Okay, I feel better now. Alright, so this slide points out for it. So let's say a system did 250 with a decimal point joules of work on the surrounding, but it gained 200 joules of heat. What's the delta E for the system? Alright, so if it did or spent 250 joules of work on the surroundings, does that mean that it lost or gained energy? Right, it lost, so it should be positive or negative? Negative. So negative 250 with a decimal point. So that's work. But it gained 20 joules of heat. If it's gaining joules of heat, is that positive or negative? Positive. Perfect. So 200 joules. So this is just simple addition to figure out what the internal energy change is. So negative 250 plus 200 is what? Negative 50. Alright, so this is addition and subtraction. So how to figure out sig figs? Right, look at the place. This is 250 with a decimal point, so the 0 counts. This one, 200, also has a decimal point. Just didn't write it. So, should I just leave it, which is 50 with no decimal point? No, you're right. I have to put a decimal point saying that this 0 counts as well. So, it becomes 50 joules with a decimal point, negative 50. So that's the answer for this first problem. Alright, look at the second one. Now let's say that 189 joules of work was done to the system and it lost 100 joules of heat. What is the delta E for the system? Alright, so if 189 joules was done or added to the system, is that positive or negative? Positive. So positive 189. And it lost 100 joules of heat. I think there's supposed to be a decimal point there. I can't tell from this angle. Whoops, I left off my decimal point. That's a bummer. Alright, I'm going to go ahead and add that in really quick. And cheat. Alright, so plus 100 joules of, and it lost 100 joules of heat. So if it lost 100 joules of heat, is that positive or negative? Negative. Alright, so 189 plus negative 100 is what? That is 89. So it's a positive value. Now remember, for this one, technically, well, no, I could have left it off and it would have been fine. I'm going to take it back off because here's the reason why. Alright, so, nope. No, it would mess it up. I'll put it back. Oh, that's way wrong. Alright, because for this one, these three sig figs count, so that means it goes all the way to the one spot. If I did have a decimal point here, it would go to the 100s spot, and so because of that, I want my decimal point, so that way it tells it that I want it to count in the one spot as well. So 89 joules is the answer for it. Ultimately, we still have a whole number, but I just wanted to make sure that it's clear what I was looking for. Alright, last one. Finally, let's say that the system didn't do any work, but it gained 50 joules of heat. What is the delta E for the system? Alright, so if it didn't do any work, did it lose or gain energy? Nope, we just write 0 for W at that point, just because nothing has happened there. But it gained 50 joules of heat, so what's the change of internal energy? Well, if it gained 50 with a decimal point, I remember to fix that one, and didn't do any work, well then it just gained 50 joules. So the answer is just 50 joules of energy. We don't count the 0 for sig figs, so don't worry about that one. Alright, so hopefully that was some good warm-up practice for you guys. We're going to start thinking about, as you start thinking about your material, make sure you're keeping track of all of your math as well. Alright, let's look down at the exothermic versus endothermic section really quick. Alright, exothermic versus endothermic. Talked about a lot this yesterday. Alright, so melting ice cubes from the point of the ice cubes, is that an endothermic process or an exothermic process? Remember, if you're going from a solid to a liquid, you have to absorb energy. So if you're absorbing energy, is that endothermic or exothermic? Endothermic. Good job. Alright, firecrackers going off. So from the viewpoint of the firecracker, is that exothermic or endothermic? Hopefully you know, because hopefully you've never actually done this, but if you've held a firecracker in your hand whenever it went off, you'll notice that it gave a lot of heat or a lot of energy. So hopefully that's never happened to you. It's a really bad day. So that's exothermic because it's giving off heat and energy. Burning wood, is that exothermic or endothermic from the point of the wood? Exothermic, because the wood is chemically changing and it's giving off heat and energy and light. So that's exothermic reaction. Cooking an egg, from the viewpoint of the egg, is that an endothermic process or an exothermic process? Endothermic, because remember, your egg, the egg white portion, is clear, and as it's absorbing the heat energy, it starts to change its consistency. It turns all white and puffy. So it's absorbing energy to cause that chemical change. That's how come you have to cook eggs over a stove, is because you have to give it heat, otherwise it won't cook properly. And there's other ways to cook eggs as well. But that's the example of cooking food. It's absorbing energy, so it's an endothermic process. Alright, evaporation of water. This is a little bit trickier. So remember, water with evaporation goes from a liquid to a gas. So if it's going to go from a liquid to a gas, is it absorbing energy or losing energy? Going from liquid to gas. Well, it has to gain energy, because remember, gas has more energy than a liquid, so it has to absorb energy for it to go from that one state of matter to the other state of matter. So, if it's absorbing third energy, is that endothermic or exothermic? Endothermic, perfect. Alright, so hopefully that kind of helps you to kind of review and to kind of think back over it. We talked about calorimeters yesterday. We went over the terms and definitions yesterday, so make sure you're still studying them, even though I'm not spending a lot of time with your classwork on them. But just make sure that you're studying, that you're paying attention. So like we've been talking about, what is the SI unit of energy? Joules. Whenever we're talking about endothermic versus exothermic reactions, which one is the products with the reactants, when they produce the product, but they also produce heat? That's what? Exothermic or endothermic? That's exothermic. What if you have to add heat into the reactants in order to make your products, like cooking an egg? That's endothermic. So we've been talking about from the idea of with the problems earlier of systems versus surroundings. What's the system in thermodynamics? That's the point of the universe being studied. What is surroundings? Everything else, basically, but for all practical purposes, it's just the rest of the room. So make sure you are studying and reviewing all of your terms, like the ideas of different types of energy. What's the energy of motion? Kinetic energy. What's the energy with forces acting on an object? That's potential energy. So make sure that you are still focusing and you're still working on it, so that way you're not just forgetting your term just because it just wasn't assigned for classwork. Alright, so what is specific heat? Well, I kind of talked about this, but we're about to use it again. Specific heat is the substance is the heat required to cause a unit rise in the temperature of a unit mass of the substance. We went over the equation already for it, so just make a note for it to help you out for it. Alright, and then what is the device we use to measure heat flow? A calorimeter. So make a note of that. So calorimeter is how you're supposed to say it. So make a note for that, that's how you're supposed to say it. Look at the diagram really quick yesterday, and we talked through the problems, and then I ran out of time. So let's go through this again, just so it's a little bit easier. That with a calorimeter, what scientists do is they take a metal, and they heat it up to a certain temperature, and then they chuck it into or throw it into this calorimeter. On the inside of the calorimeter, they have a water at a certain temperature, and they know how much water is there. They also know water specific heat. Like I said, you'll probably memorize it. You don't have to, but you probably will, just because you're going to use it so much. So, whenever they do that, the heat from the metal becomes lost in the water. Because remember, heat always flows from higher temperatures to lower temperatures. Eventually, you'll reach the area of thermal equilibrium. That's whenever the thermometer isn't rising anymore, and that's whenever it pretty much stops. Now, if they let it sit here, it will eventually start to go down. But that's at thermal equilibrium. That's whenever the temperature is no longer rising. The water and the thermometer are at equal temperatures. From this point, we can actually calculate out and see, okay, what's that change of temperature for the water? What's the change of temperature for the metal? And we can find out the metal specific heat. And scientists do this because sometimes they might not know what type of metal they found. And you can use specific heat to help identify the metal. Alright, the equation we use for this has to do with the first law of thermodynamics. Because remember, the heat gained by a system has to equal the heat lost by a surroundings. And so scientists take this and they go, okay, if we take a piece of metal and throw it in water, the metal will lose heat to the water. So the metal's losing heat, and the water around it is gaining heat. But rather than using this equation, equation like this because very rarely do we know how much heat the metal has and we don't know how much heat the water has. Very rarely we don't know it this way. So because of that, we have to switch over and substitute out for this equation. Since Q equals Cm delta T, we can swap it out. So Cm delta T, the negative side of the system side because it's losing heat, plus the positive Cm delta T. So this is the positive side, we don't really put the positive sign there. It also comes in your book, it doesn't have it there because it's understood, okay, if it's if there is no positive sign, then it's positive value. You do have to have the negative sign on this side. You have to have it because since this one's temperature is going down, will it be a positive or a negative temperature change? It'll be negative because it's going down. So you're going to have your negative signs cancel out. That's why it's important to have it there. All right, let's practice with this equation now. So I'm going to rise to the top so I won't forget. So negative MC delta T equals positive MC delta T. All right, so let's practice for this one. All right, so on page 83, an experiment to find the specific heat of lead. 49.8 grams of lead at 100 degrees Celsius was placed in a coffee cup calorimeter containing 75 grams of water at 21 degrees Celsius. The final temperature of the mixture was 22.7 degrees Celsius. What specific heat of lead? And then it also tells you assume no heat is lost. There is a tiny amount of heat, lost to the surroundings. But scientists know that, okay, most of the time it's so small it doesn't matter. So just assume that there is no heat loss, that all the heat lost by the metal was absorbed by the water. Alright, so let's figure this out. So let's plug in our variables. The best thing to do is to just plug it in, kind of like with the combined gas law, how we did that previously, how we would plug it in as we go. That's also the same idea. Did I write it right where the bar is? I did. Alright, let me write it up higher. So neg MC delta T equals positive MC delta T. Okay, I'm just going to draw a line here so that way I won't forget the bars there. Okay, so I believe I should fix it now. Yeah, that's annoying. Okay, but hopefully that should fix it. Alright, so let's plug in our variables for it now. Alright, so let's look at the lead first. Alright, so how many grams of lead do I have? Alright, 49.8 grams of lead. So that's what I'm starting off with. What specific heat of lead? We don't know, this is what we're finding. So we see changing of temperature of lead. Okay, so how do I find out the change of temperature? It tells me that it was started at 100 degrees Celsius, and at thermal equilibrium it stopped at 22.7. So don't just see, hey, I see 21 degrees Celsius. Nope, remember it's talking about the water, so pay attention to what you're reading about. So it went from 100 degrees Celsius to 22.7 degrees Celsius. So remember, it's final minus initial. So it's 22.7 minus 100. This is so that way you develop good habits to get your negative sign. So this is negative 77.3 degrees Celsius. That's the temperature change for the lead. So 77.3 degrees Celsius, negative. And the last thing I need is specific heat for this side. Alright, so water side now. Water, it tells me, for water, it started off with 75.0 grams. Gonna run out of room, that's a bummer. 4.18 joules per gram degrees Celsius is specific heat, because again, the table tells you that, plus you're gonna memorize this eventually. Temperature change in the water, it went from 21 degrees Celsius to 22.7 degrees Celsius. Alright, did it go up or go down? So should it be a positive or a negative temperature change? Positive, because it went up. So finest minus initial though, so 22.7 minus 21 degrees Celsius, that comes out to 1.7 degrees Celsius. So that's the temperature change. I'm going to write it down here because I'm out of room with bars. Alright, so how do I solve this? So I have to get C by itself. Don't forget though, you have to put your negative sign, so that way you can remember to move it as well in a second. Now remember that these negative signs cancel out each other. Because remember, a negative times a negative is another negative. So, sorry, negative times a positive is a negative value. So negative times a negative, or negative divided by, keep saying negative times negative. Negative times a positive value will give you a negative number. A negative divided by another positive number, or have a negative value and a positive number in a division problem, will also give you a negative. If I have a negative times a negative though, that gives me a positive value. So that's the reason why you have to remember, okay, I have a negative number, temperature change, I have an understood -1 multiplied by it. So they will cancel out whenever I shift them and move them over. Alright, so moving everything down here to the bottom, that I have I have negative 77.3 degrees Celsius with times the 49.8 grams, and all that has a negative sign attached to it, so that way they cancel out for it. Whoops, dropped my clock. So that gives me the specific heat by itself. So what to do to solve for this problem is you want to take 75 times 4.18 times 1.7, sorry, it's slightly scattered all in here, I ran out of room, divided by -1, divided by -77.3, divided by 49.8, so your negative values will cancel out each other. Alright, the answer you get for this is you're going to get a positive value of 0.138 joules per grams degrees Celsius. Alright, so that becomes the answer for this problem. I'm going to type it into the calculator so I can see what the unrounded answer is, since the book didn't give it to you. So 75 times 4.18 times 1.7 divided by -1 divided by -77.3 divided by 49.8. Alright, so the unrounded answer that you get in your calculator, I'm going to write it over here, I'm running out of room, is 0.13844, but because 3 sig figs, and this is temperature change, so don't really worry about that one a whole lot, because we started off with 3 sig figs. So you'll notice in your book that it was 21.0 degrees Celsius, 22.7 degrees Celsius. So just because you found the difference between them, don't let that stress you out. You want to go with what your starting values were. So this started at 3 sig figs for the temperature change. You want to keep that as 3 sig figs mentally in your head. Alright, and then 3 sig figs, 3 sig figs, 3 sig figs should be your answer for it. Now remember, for specific heat, it's joules per grams degrees Celsius. So make sure you write out your units that way. And that becomes the answer for it. As a side note, your specific heat is always a positive value, so if you got a negative number, it means you messed up somewhere. So just be careful as you're going through it. You don't want to accidentally mess it up. So you should always have a positive value for a specific heat. Alright, let's practice with this some more, because I know this needs probably a little bit more help. So, switching back to my practice problems. Whew. I'm getting winded, I'm talking too fast. Alright, we did 4, 5, and 6 yesterday, so let's do 7 and 8. Again, I think you can read these, so I'll read the first one aloud, because I know it's kind of hard to see, but I believe you can read them on your screen. Alright, so 7 and 8. A piece of silver at 120 degrees Celsius is put into a calorimeter. Inside the calorimeter, well, let me pull that back out then. Nope, I'm going to have to zoom out a little bit. I'm sorry. Okay. It looks less zoomed in on my screen than it does on the actual slide. Nope, not quite. Okay, let's see if that works. Okay, I think that might be close enough. Let me try to slide it over a little bit. Okay. No. Let me slide it over some more. Got to check this. That's probably close enough. Okay, so it's 100 with with a decimal point for number 8 with the joules, so I think that one's a little bit cut off. Alright. Alright, so a piece of silver at 120 degrees Celsius is put into a calorimeter. Inside the calorimeter, 100 grams of water at 25 degrees Celsius. Water at 25 degrees Celsius. The final temperature at 30 degrees Celsius. What's the mass of the silver? So we're finding mass. So pay attention to what you're asked to solve for in this problem. So you go ahead and pause the video. Try to see if you can work it out. I'm going to zoom out just a little bit. If you get stuck though, come back. Alright, so let's go ahead and let's solve for this one. Alright, so I'm going to slide over so that way you can see me solve it as well. Alright, so for this one, it's a piece of silver at 120 degrees Celsius is put into a calorimeter. Now, you might think, well, Ms. Morris, you didn't give us what specific heat of silver is. That's because your textbook tells you. So if you flip back to page 81, you'll notice the specific heat of silver is 0.24. So, write it over here so I won't forget. Okay, good, you can still see me. Alright, so for specific heat of silver, 0.24 joules per gram degrees Celsius. So that's specific heat of silver. What's the mass? Right, so that's what we're trying to find. So I'm just gonna write M so y'all remember to find it. Alright, temperature change for silver. So it went from 120 degrees Celsius, and then the final temperature was 30 degrees Celsius. So it went from 120 to 30. So subtraction, remember, is final minus initial. So 30 minus 120. So that becomes what? 70. Negative 70 specifically for it. Sorry, 90. Negative 90 specifically. So negative 90, I'm not going to worry about sig figs for right now. So I'm just going to leave it at just negative 90. And then I'll figure out sig figs based on my starting calculations in a minute. So negative 90 degrees Celsius. Alright, water. How much water did I start off with? I started off with 100 grams of water. Water specific heat, 4.18. Like I said, you're going to memorize that. Joules per gram degrees Celsius. Alright, temperature change for the water. Went from 25 degrees Celsius to 30 degrees Celsius. Is it positive or negative temperature change? Positive. So 30 minus 25 is 5 degrees Celsius. So that's the temperature change for the water. So, remember, all of this is negative, so when my negative values cancel out, I gotta get mass by itself. How do I get mass by itself? Right, I divide. So it becomes negative 0.24 times negative 90 divided all into the top portion. So the whole thing together becomes 100 times 4.18 times 5 divided by negative 1 divided by 0.24 divided by 90. The answer comes out to 96.7592, and then it just keeps going for it. So, with proper sig figs, I'm looking at my starting values, what I started with. I started off with 120.0 degrees Celsius, so that's 4 sig figs. Put into a calorimeter. The calorimeter has 100 with three sig figs, because 100 has a decimal point, and 25 degrees Celsius. The final temperature was 30 degrees Celsius, so all of those have 3 or 4 sig figs. Since I'm going off multiplication and division, how many sig figs should my answer have? If I started off with 3 or 4 sig figs, it should be 3. So this becomes 96.8 grams. Remember, we were asked to find mass, so it's grams specifically. Alright, so let's practice with the next one, problem number 8. So hopefully, if you got kind of stuck in that first one, you can kind of see, okay, I think I know what I'm doing now. Alright, so a 25 piece of iron at 100 degrees Celsius is put into a calorimeter. Inside the calorimeter is 100 grams of water at 25 degrees Celsius. The final temperature is 27. What's the specific heat of iron? Alright, so let's plug in our variables. So the metal is the first side we're going to do. So the mass, what is the mass of the iron? So 25.4. We don't know specific heat. Temperature change. It went from 100 degrees Celsius to 27 degrees Celsius. So 27 minus 100 is what? Alright, you should have said negative 73. So negative 73 is the temperature change. I'm just going to write C's, I'll forget C's there. Alright, so the mass of the water is still 100 degrees Celsius. Specific heat of water, 4.18 joules per gram degrees Celsius. Alright, temperature change. It went from 25 degrees Celsius to 27 degrees Celsius. So 27 minus 25 is 2. Perfect. So 2 degrees Celsius temperature change. Alright, so, oh, forgot my negative 1. Alright, so how do I get specific heat by itself? Alright, I bring everything on the reactive side or on the metal side and put it down. So it's negative 25.4 grams with negative 73 degrees Celsius, so negative 1, understood. Alright, so 100 grams times 4.18 times 2 divided by negative 1 divided by 25.4 divided by negative 73. That all comes out to 0.45086. Now, looking at my values, how many sig figs should I have? So I started off with 25.4 grams, so that's 3 sig figs. 100 degrees Celsius with a decimal point, that's 3 sig figs. Inside the calorimeter, there's 100 grams of water, 3 sig figs. 25 degrees Celsius, 27 degrees Celsius. Now there's only 2 sig figs in 25 and 2 sig figs in 27. So this is on multiplication and division. What should my answer be? 2 sig figs. So this answer becomes 0.45 or 0.5 if you want to be technical for it. Can't write low. Now remember, this is specific heat, so what's my units? Joules per gram degrees Celsius. Alright, so that's some good practice for that. Because you had to pause the video to solve this out, I'm going to go ahead and stop because you probably spent time solving the practice problems at the beginning and solving these now. So we'll go ahead and we'll stop here for you. Alright, your homework for tonight is you're going to, let's see, didn't quite make it as far as what I wanted to, so let me find something that I want you to do. So that you're not wasting your time. You know what? You can do on page 92, you can do, so on page 92, the problem section, you're going to do just problem number 2. So, make a note for that one, that on page 92, because I don't really have any reading for tomorrow. If you'll notice, we're going to start a lab tomorrow, but don't just start it, come in because I want to talk to you because you're going to go over a lot of review, and I want to make sure that you understand how to solve this type of problem. I need to give you instructions for the lab. Plus, other things might be happening tomorrow, so not telling you for sure, but you should be studying tonight. So study, and then also do on page 192, problem number 2. It'll give you practice with calorimeters. So if you get stuck, be sure to pay attention. So don't just watch the Abeka video tomorrow with the lab. Be sure to come in, watch part of it, watch the YouTube video, and then you can jump and go watch the lab as well. But make sure you log in tomorrow. I can give you some last minute instructions, go over homework, and review in case there's stuff tomorrow. So that way it'll help you get ready for it.